Okay, in this video, we're going to cover section 5.2, and that's continuing with trigonometry. Actually, in this section, we're going to define the trigonometric functions, also known as circular functions, which will be the name of which will be more clear why we use that term. Now, it's not widely used, but it is used because we're going to define the trigonometric functions in terms of the unit circle rather than the standard way of defining it in terms of right triangles. Although we will also in chapter 6 look at this other approach to defining the trigonometric functions, and it turns out that these two approaches are equivalent, and it's useful to have these two perspectives. So let me share my screen. Okay, so in 5.1 we took another look at the unit circle, and typically the unit circle is thought of as living in the plane as a two-dimensional object, but it turns out that we can think of it in an even simpler way. We have this one-dimensional picture of a circle, and I try to give you some more advanced perspectives on how we do this, using topology and stuff like that, and looking at like a unit interval and gluing the endpoints to give a circle. So that's how this one-dimensional feature or aspect of the unit circle arises. So the idea is that, so first of all, let me just write down this section. This is 5.2, and this is trigonometric functions of real numbers. Of course, you can do all this with complex numbers, and it gets a little more interesting, but we're just going to look at the real number case for now. That's actually all we're going to look at. But if you go further on, you'll study all the functions that we've been looking at of a complex number, a complex variable. So the idea is, let's see if I remember how to do this. So you have, there we go. You have the circle, and we generally think about it as living on the plane, but if you take a point, this point right here, and just fix this point, so this point is 1, 0, as a reference point, and if we just think about our universe as just the unit circle itself, we live on the unit circle, we can only move on the unit circle. We can't look side to side. All this right here and all this out here is empty space. It doesn't exist from our perspective. We're just on the unit circle. We can just kind of move in this direction or in this direction. And if that's the case, then really we only need a single number to specify, a single real number to specify a position on this circle, and namely the arc length, this assigned arc length, really, but not quite. So just the assigned distance or arc length that you travel. So if you're traveling in this direction and you stop here, this length, well, the arc length just gives you a measure of how far you are from this reference point. So given this reference point, this reference point is just, it serves the same function as the origin does in the plane. You just fix a point and then you measure positions relative to that point. In this case, we can just get away with one number. That's why it really is just a one-dimensional space. Because if you recall, dimension is roughly the number of numbers you need to specify. The number of numbers you need to specify a position in a space. So in 2 dimensions, you need 2 dimensions. If you're in the plane, you need 2 numbers to specify a position in the plane. 3 dimensions, you need 3 numbers to specify a position in the 3-dimensional space. But the circle, we just need 1, and that's why it's really just a one-dimensional object. And so if you travel some distance, then maybe this distance is t, In this case, we're looking at positive numbers. You land on the point, but then you can go back to thinking about the circle as living on the plane, and there's a correspondence between this point is viewed as a point in the circle, but then more in a greater picture viewed as a point in the plane. So given a number t that represents some length you travel along the circle from this point, reference point, it will determine a point on the plane / circle. So there's this way of going. In section 5.1, we looked at ways of going back and forth between these two ways of viewing points on the circle. And our convention was that if I give you a positive t value, that means you travel in this direction. So you travel in this direction. And if I gave you a negative number, it means you traveled in this direction. And we found that two different values of t can give you the same point on the circle. So really simply, if t is equal to 0, that means you just stay at the reference point. You don't move any distance along the circle. But if t is equal to 2 pi, that means you go all the way around the circle counterclockwise and end up at the reference point. So these 2 points, these 2 numbers, they determine same point on circle. So this correspondence between ordered pairs and these arc length numbers isn't unique. I can give you, so in other words, if we're thinking about these in terms of functions, this is not an injective function because I can find 2 values of t. So we're thinking of like a mapping. There's a mapping between real numbers and points on the circle. We set this up, and that was the point. That was our whole discussion in 5.1 was kind of fleshing this function out. This, going through the process of really defining what it means to have this mapping from the real numbers to the points on the circle. And what this basically says right here is that this function's not injective. You can't, if I give you 2 different real numbers, t equals 0 and t equals 2 pi, and these are different numbers, they'll determine the same point on the circle. So that was really a brief overview of what we did in section 5.1. So now we're going to use this this picture of the unit circle to define the trigonometric functions. So here's the definition. So I'm going to define all of the trigonometric functions. So we let t be any real number. So t is just some real number. I give you a real number. And this will determine a point on the circle. You travel along the circle. If t is positive, you travel clockwise. The distance of t is negative, you travel, or no, if t is positive, you travel counterclockwise the distance of t, and if t is negative, you travel absolute value of t clockwise. And then you'll land on some point on the circle, and then we'll call that point pxy. And this is we're going to let this be the terminal point on the unit circle, determined by t. And then we can just set up a bunch of definitions. So sine of t, remember this colon and then this equal sign means I'm defining what this string of symbols means. So sine of t doesn't have meaning, but now I'm going to give it some meaning. It's defined as y equal to y. So in other words, I give you a point t, I give you a real number t. It determines a point x, y in the unit circle. And sine t is just you pluck out the y coordinate. So that's what it's saying. Just you take the y coordinate of p of x. Then we have cosine. Separate these. Cosine of t is defined to be x. So again, you just take the x coordinate. You're given t, determines a point on the unit circle, and then you look at the x coordinate, and that's defined to be cosine t. And then we have tangent of t, and that's simply just the ratio of the y coordinate to the x coordinate. And then the other cosine functions are like they're in a sense just they're actually just reciprocals. So cosecant t is 1 over y, so this is the reciprocal of sine t, and then you have secant t, that's defined as 1 over x, so that's reciprocal of cosine cosine t. And then we have cotangent t. I'm going to put parentheses around it so the t's don't get mixed up. And that's defined to be the reciprocal of tan t, but that should, which is the same as x over y. I should say here, you know, you have to be careful about this number t you're given, because if it's such that the x coordinate is 0, this doesn't make sense. So you have to stipulate that x is not 0. Here you have to stipulate that y is not 0. Here you have to stipulate that x is not 0, and then here you have to stipulate that y is not 0. So you have to be careful about that real number t you're given. You have to make sure that that is not, you have to be careful about the point it determines. So just watch out for that. So those are the trig functions. They're also called circular functions because they're really just defined in terms of the unit circle. So there's no reference to angles or angles or triangles or anything. The idea is I give you a t, let's just say it's positive. And then, so maybe the t value lands you over here or something. Oops. And that, we'll call that point xy. And you have the sine and cosine are kind of, if we're just thinking about sine and cosine, because the rest of these trig functions are defined in terms of sine and cosine. So if you know the definitions, and if you understand, not that you know the definition of sine and cosine, but if you understand the sine and cosine functions and what they are, what they represent, and you know the definitions of the rest of them, then you know all the trig functions. So there's a difference between knowing the definition and like having an intuitive understanding of these functions. So the cosine and sine are just really like projections. So you have this point and you can project it down to the x-axis, and this will be x, which is cosine of t, and then this right here, this you take the point, you project it down to the y-axis or onto the y-axis, and that point on the y-axis is your y coordinate, which we're just saying is y, and that's equal to sine of t. So let's look at some examples. So this is example 1. And this is part A. So we're given a t value of pi over 3. And always have, it's always good to write down our unit circle with all the basic arc lengths, I guess, is what you would call them. So let's draw our unit circle. So we have the reference point that's 0, 1, and that kind of corresponds to 0 or 2 pi or even 4 pi, etc. Then we have the point, let's see, it's root 2 over 2 over n 1/2, and this corresponds to pi over 6. Then you have like this midway point in the quadrant. This is where the coordinates are the same. So it's root 2 over 2, root 2 over 2, and this corresponds to pi over 4. And then you have pi over 3. Or you have the point right here. This is when you take, it's like pi over 6, but you just flip the coordinates. So this one right here will just be 1/2 root 2 over 2. Let me just make sure I got this right, because sometimes I forget myself. Okay, actually I did make one mistake. So this is, it's a good thing I checked. So we have, this is not root 2. This, oh, that is root 2. Fix it. It's root 3. So this is root 3. This is root 2. And this is root 3. And then this point right here is the one that corresponds to pi over 3, which is this arc length that we're interested in. So a table like this, I'm going to pull this up now. You should remember this table. You don't need to really, if you remember the first quadrant, you can kind of determine what the other points are. So if you, here's the table. A table like this, it's a lot scarier than it looks, but it's not that bad actually. So let me just open this up. So you have, so here's our reference point on 0, that corresponds to 0 or 2 pi. Then you have pi over 6, which corresponds to the point root 3 over 2, 1/2. Then you have pi over 4, which corresponds to root 2 over 2, root 2 over 2. And then you have pi over 3, which is the one we're interested in. That corresponds to the point on the circle when viewed in the plane as 1/2 root 3 over 2. Oh, and then of course this one, you have pi over 2, which corresponds to the point 0, 1. But notice, so it looks like if really all you need to memorize is these, even though this table looks a lot more horrible than it is, it's not that bad. So if you remember that rise this first quadrant, you can kind of know what the other ones are going to be. So if you see like pi over 3, it's 2 pi over 3, but there's a pi over 3 in here. That means the coordinates are going to be similar to the ones in the first quadrant. Notice the difference is just you put a negative sign in the x-coordinate. And that makes sense because we're out to the left of the origin. And then you have 3 pi over 4, but there's a pi over 4 in that. And notice the coordinates are almost the same. You just have to put x negative number on the coordinate. So once you get used to like once you get used to the correspondence between the arc length you're given and what quadrant you're in, determining those points is pretty easy. They're going to be, you're just going to put negative signs in appropriate places. So like if you're in the second quadrant, it's just these same points in the first quadrant, but you just put a negative sign on the x-coordinate. And here are the corresponding arc lengths that you travel. If you're over here in the third quadrant, the x and y, when you're in the third quadrant, the x and y coordinates are both negative. So you just, if you just take these points in the first quadrant and you just put negative signs on the x and y coordinates, see? And here are the corresponding arc lengths to travel. And the same thing over here, you can play the same game. Just so it's a matter of like just putting the a negative sign on the appropriate coordinate. So it's always good to draw this circle because then it'll help you memorize these numbers and the correspondence between these arc lengths and these points on the circle. So we're interested in pi over 3. So we want to calculate the trig functions. We want to know sine of pi over 3, cosine, and I'm just going to go through the three basic ones, and I'll leave it to you to figure out the other ones. I'm just going to do sine, cosine, and tangent. So we have sine pi over 3. Remember, that's the y coordinate. So this is the point we're interested right here. So the y coordinate of that is just root 3 over 2. Cosine of pi over 3. This is going to be the x coordinate. That's just 1/2. And then finally, tan of pi over 3. That's going to be the y coordinate over the x coordinate. So it's 3/2 over 2 divided by 1/2. And if you flip things around and cancel, these 1/2 will cancel. You'll just get root 3. So now part B. So we're going to use. So part B is to calculate the trig functions when t is equal to pi over 2. So again, even though this, I'm not going to go through it, but I advise you to, like, every time you work on a new problem, even though this is the same example, we're still working on even though this is the same example, we're working on a different part. So draw that circle just to commit those values to memory. I'm not going to do that for the sake of time, but actually I didn't finish the table, so I had to add a little bit to this. But yeah, just keep drawing this table over, or this unit circle over and over and over, and you'll just get used to what these values are. So this point right here is 0, 1, and that corresponds to pi over 2, which is the angle we're interested in. Or not the, I mean, it is in a sense an angle. That will become more clear when we go to chapter 6, when we define trig functions as, or when we define trig functions in terms of triangles and angles. So I might occasionally make a blunder by saying this arc length is, I might refer to the arc length as an angle, and they're really almost basically the same thing. So but you know, since we're in chapter 4, if I say angle, I mean arc length. But as I said, they end up being the same. So this is the point that we're interested in. So we're given the t value of pi over 2, and this is the point. So let's draw that down here. So that's 0, 1. So this is the x coordinate and the y coordinate. So sine of pi over 2 is the y coordinate, which is 1. Then we have cosine of pi over 2, which is the x coordinate, and that's 0. However, this tan, this is where we have to be careful. This is an example where we have to be careful because tan of pi over 2 is not defined. Because you can't divide by 0. There's no way of extending the function to a value. There's no way of extending tan to values of like pi over 2. So we just have those two values. However, cotangent will be defined because it will be x over y, and so we can divide by y, which because we have y is non-zero. So here's the table. I'll just throw the table up again. This is from the book. And here's some like typical t values, and then there's the corresponding trig functions at those t values. These bars mean that they're not defined at those values. And here's the graph that I drew already. So just some observations. We want to look at we want to look at make an observation on the domain of these trig functions. Let's make an observation on the domains. So sine and cosine. So yeah, let me just say the function and then the domain. So we have sine and cosine, and sine and cosine have domain of all of R. You can plug in any real number. There's no restriction because there's no division by 0. There's no square roots involved or anything. It's just taking the X or the Y coordinate. For tan and secant, we have that the domain is all numbers. So all real numbers except the ones of the form pi over 2 plus n pi for any integer. So if I give you a t-value of this form, you can't plug it into tan or secant. Otherwise, you can plug it in there. And then finally, I have cotangent and cosecant. And again, we have a similar restriction. It's not quite the same, but similar. So all of R except for all the numbers of the form n times pi for any integer n. So n is some integer. So if I hand you a t-value that's of this form, some multiple of pi, you cannot plug it into cotangent or cosecant. Otherwise, you can. Here's like I guess a little mnemonic. I won't draw it, but I'll show you. I don't. For some reason, my brain doesn't work this way. My brain just doesn't use mnemonics. I just somehow remember things after a while. But if you're the sort of person who does use these, here's maybe something that's helpful. So if some questions sometimes you don't need to know the exact value of the trig function. You just need to know whether it's positive or negative. And there's this way of memorizing it. It's the one, I guess it's right here. All students take calculus. All students take calculus. So this tells you where the functions are positive or negative. So if your t-value is such that you're in the first quadrant, then all the trig functions are positive. All of them. If your t-value is such that it lands you into the second quadrant, the only one that's positive is sine and its reciprocal, cosecant. The rest are negative. If your t-value is such that you travel along the circle and end up in the third quadrant, your tangent function and the reciprocal function, cotangent, are positive, but the rest are negative. And then lastly, if your t-value is such that you travel all the way around the circle and land in the fourth quadrant, the only trig functions that are positive are cosine and secant, which is its reciprocal, and the rest are negative. So if we're it turns out these are actually continuous functions, but I don't want to really discuss that right now. But we have these functions, and we can ask what sort of properties do these functions have? And one natural question is, do any of them have symmetry? Are they even or are they odd functions? And it turns out that they do have symmetry. They have nice symmetry, actually. So let's just look at an example. So I won't prove all of these, but I'll just maybe prove a couple. So let's draw a unit circle, and then suppose we're given t-value. So let's say it's just positive for simplicity. I give you a t-value that's positive. It means you land here. Okay. That determines the point x, comma, y. Well, if you travel, it's supposed to kind of be along the arc. It's not perfect, but if you travel, if I give you negative t, that means you start at the reference point and travel the same distance to it. So maybe right here. And notice these points are kind of like they're like opposite. They're not diametric, but they're kind of opposite to each other. So we can easily deduce the coordinates for this one, they will be x and negative y. So you just kind of flip over the x-axis. That's what's going on here. So this corresponds to t, the t value you started with, and this corresponds to negative t, which is, of course, negative. And so what this means is that if you take sine of t, you get x, but if you take sine, or sorry, you don't get x, you get y, because sine is the y coordinate. But if you take sine of negative t, you get negative y, which is the same thing as sine of negative sine of t. So what this means is that sine of t is an odd function. So sine of t is an odd function. Now, notice in this case though, if you look at cosine of t, it's equal to x, and cosine of negative t is also equal to x, which means this holds. So what this implies, or what we can conclude, is that cosine of t is an even function. And you can do similar proof for the rest of the functions. So let me just summarize this. So we have even and odd properties. So the even functions, trig functions, are going to be cosine, and actually just cosine and secant, the secant function. The odd ones are going to be sine, cosecant, sorry, it's not the abbreviation, cosecant, and tangent and cotangent. So what this means is that we have the following table. So we have sine is equal to negative sine t. And then we have cosecant of negative t is equal to negative cosecant of t. Then we have cosine of negative t is just cosine of t. Secant of negative t is just secant of t. And finally, tangent of negative t is equal to tan. Or not finally, we have one more actually. So this is just saying that tangent is an odd function. So tan of negative t is tan of t. And then cotangent of negative t is the same thing as negative. Oh, sorry, this is supposed to be negative because it's an odd function. So we have these various identities, and this will actually help us in calculating these trig functions. So let's look at example 2 in the book. So this is 5.2, example 2. So we want to find cosine of 2 pi over 3. What is that equal to? Well, let's draw our unit circle. No, let's not do that. Can I do? Yeah, I don't want to draw this. I want to save it. I don't want to waste time. Definitely draw on your own though. Definitely draw the unit circle. So let's see if I can. So try to pull up the book, sorry. Okay. So this is what I wanted to draw, but just for the sake of time, I'm just going to use the book. So we are interested in cosine of 2 pi over 3. So we have a pi over 3 in here. So that means it should be some variation of this coordinate. But we have to figure out what quadrant we're in. But it's clear that, so to determine what quadrant it is, we need to compare it to these values like pi over 2, pi, which isn't drawn here, 3 pi over 2, etc., and 2 pi. So we like those are the points where you shift it into different quadrants. Like they divide up the quadrants. Those 4 points: 0 or 2 pi, pi over 2, pi, 3 pi over 2, and then back to 0 to 2 pi. So we want to compare 2 pi over 3 to those values. Well, it's not hard to see that. So 2 pi over 3 is less than. It's not hard to see that 2 pi over 3 is less than pi. So it's definitely not going to be over here or here. So it's going to the point determined by 2 pi over 3 is going to be on here or on here. So the top half of the circle. But it's also clear that 2 pi over 3 is greater than pi over 3. So in other words, what we have is the following. We have pi over 2 is less than 2 pi over 3, and that is less than pi itself. So what that proves is that the point is in the second quadrant. So we're in the second quadrant. So let me pull the book back. One note all the way. So we're in the second quadrant, and so what that means is that the point, actually that was stupid because I need this stuff. The point is when you're in the second quadrant, you put a negative sign on the x-coordinate. So we just had to take this point right here and put a negative on the x-coordinate. So you get this, you obtain this. And then, of course, since the cosine is, you just take the x-coordinates, we can now finally calculate cosine. So that's cosine of 2 pi over 3 is going to be negative 1/2. Now let's look at part B. So part B is, I think it's pi. Yeah, it's 10. I'm not going to do part C. I'm just going to do part B. I'll leave part C to you. So we're looking at tangent of negative pi over 3. So negative pi over 3 means, dealing with these negative numbers is kind of, it can be a little challenging because that, it's like, am I traveling clockwise or counterclockwise? Negative number means travel clockwise. But if we use the fact that the tangent is an odd function, we can just avoid that headache completely, and we just pull the negative out of the function. So it would be negative tan of pi over 3. And then if we have our table handy, we can figure that out. So tan of pi over 3, so pi over 3 is going to be this point, and if you just remember that, all you have to do is remember that the tangent is the y-coordinate divided by the x-coordinate. And actually, we did this problem already. This ends up being square root of 3. Oh, sorry, there's a negative sign here. So negative and then negative square root of 3. So so that's part B. As I said, I'll leave part C to you. And let's finish up this section. So we determined that these are even and odd functions. And the last thing I want to introduce is some more properties of these functions, how they interact with each other in a sense. So as we already noted from the definition, it's immediate that the cosine, the cosecant, the secant, and the cotangent are just reciprocals of the other three functions. So that's one property. But more importantly, we have these Pythagorean identities, which I won't prove, but you can find a proof in the book if you're wondering why are these true. Because maybe you just don't want to accept this as true. If that's the case, then you're a true mathematician. You don't want to accept anything as true. You want a proof, and I applaud you for that. So yes, I encourage you to look at the proof if you so desire, but I'm just going to for sake of time and for our purposes, I'm just going to just write down the identities. So we have, perhaps this one is more familiar to you than the others, we have this following identity, that sine squared of t plus cosine squared of t is equal to 1. And remember, this right here, and the same applies for the rest of the trig function, is defined as sine t squared, but we prefer this notation because this is just too much. You have to use parentheses. It's just too much to write. Mathematicians are lazy, so they want to write as few things, use as few symbols as possible. So we have tan squared of t plus cosine squared of t is equal to 1. Then we have tan squared of t plus 1 is equal to secant squared of t. And then finally we have 1 plus cotangent squared of t is equal to secant, or cosecant squared of t. And as I said, there's a proof, and then there's some, I won't go through these, but there's some really simple examples you can go through if you don't quite understand these. And of course, if you ever need help with any of these things, just send me an email and we can set up a Zoom. So that's all for today. This is section 5.2, and then I will upload at some point, maybe tomorrow, lecture on 5.3.